Good evening, everybody.
Good
So,
evening, sir.
am I audible? Okay.
Yes, sir.
Okay. So,
Good evening, sir.
good evening, good evening, good evening. Okay. So, some people have complained that they are not able to write the thing. So, you have to just tell me that, sir, okay, wait, and then I will remove the or delete the all part of, erase the all part of board. Okay. So, there is not any problem. We can wait 1 minute, 2 minutes. There is not any problem. But obviously, you have to write what only those things which I am explaining on board, not everything what I am telling you. It is next to impossible that you can write it. Okay. So I just request you whenever you have this sort of problem, and sometime if I am very fast, or then you can easily tell me, sir, please be little bit slow, and we can do it easily. Okay. Because it is very difficult that what is your mode of uh, learning. We I cannot see what is your or body language in the class. Okay, so you have to just communicate us that, sir, little bit slow, or please wait for 1 minute. Okay, there is not any problem.
Yes, sir.
Okay. Okay, so we can do it easily. Okay, so let's start. So we are at the next level of quantum mechanics. We have prepared all our tools, and now we will just go for to make rules and regulations of quantum mechanics via postulates. And these postulates are so important, and in fact postulates are everywhere. It is in the statistical mechanics, it is in classical mechanics, but quantum mechanical postulates are so popular, and it's so straightforward postulates that if you understand all these postulates, you can easily apply on the quantum mechanical system. And it is very important to learn the postulates before applying it to any system. So there are 5 postulates, and all postulates are well defined. There are a lot of discussion about any postulates, but postulates 4 have still a lot of discussion on it about postulates 4. So we will also include postulates 4, but postulates 3 and postulates 5 are the most important postulates for your examination point of view. But yes, every postulates are just correlated and to each other. So let's try to go for today I will try to cover postulates 1, postulates 2 and postulates 3. Although postulates 1, 2, 3 are different postulates, but what we can do, we can easily talk about everything once we will understand the postulates 3. So when we will go for postulates 1, it is just a definition. Postulates 2 is the some application, but postulates 3 will give you the complete information about the system, and when we are talking about this thing. So let's try to go for the postulates 1, 2 and 3. So first we will go for postulates 1, and every postulate has its name. So first we have this is postulates 1, and this is state of a quantum mechanical system. State of a quantum mechanical system. Obviously, the system, you have n number of system. For example, harmonic oscillator, one system. You have basically simple pendulum, another system. Hydrogen atom, another system. So you have n number of system. So system is actually the classical thing. It is not classical, not quantum mechanical. It is actually that you have to work on this particular system. You have to analyze this system. So how you will define the system? You will define the system obviously with mathematically with the Hamiltonian. So you can define, once you know the Hamiltonian of a system, you can define it. So classically, so in classical mechanics, we know the Hamiltonian And obviously the Hamiltonian is function of generalized coordinate, generalized momentum, and it will be function of time. So this is basically Hamiltonian of a system. And if you know the Hamiltonian of system, you can easily use Hamiltonian equation of motion. So we have basically del H upon del Q is equal to, or Qi is equal to minus Pi dot, and del H upon del Pi is equal to Qi dot. You have this Hamiltonian equation of motion. But in quantum mechanics, we cannot apply this thing because obviously Newton's law is not valid, because the state of a system is not, the classical state of a system is not deterministic. Means x and px is not deterministic in quantum mechanical system. And then what you have to do in quantum mechanics, in the classical mechanics, what is the state of a system is obviously x or px. This is the quantum mechanical state. Sorry, this is the classical mechanics state. Classical mechanics state is all xpx. What is quantum mechanical state? The quantum mechanical state, is defined as a psi. The quantum mechanical state is defined as psi kit, which belongs to Hilbert space, which belongs to Hilbert space associated to the system. So this is the quantum mechanical state. So obviously, if my system has generalized coordinate x, then the state belongs to that
Sir is not visible, right or not?
So this is the quantum mechanical state psi, which belongs to Hilbert space associated to the system. So this is straightforward. Means once you define the system first. So first you will define the system and you know what will the generalized coordinate. So obviously that is the classical generalized coordinate. And once you know the classical generalized coordinate, you can construct the state. And that state is known as quantum mechanical state of a system. And this belongs to Hilbert space. Obviously, if system has generalized coordinate x, then psi x kit or psi x belongs to Hilbert space that psi x belongs to Hilbert space that is associated to the system. So this is a straightforward thing. So this is a definition of a state. But what is actually first postulates? The first postulates is very interesting, and it will tell you all about if psi 1 is a state, psi 2 is a state, up to psi n is a state, then any superposition, what is the meaning of superposition? Means C1 psi 1, C2 psi 2, up to Cn psi n is also a state. If these are a state of a system, so you can have n number of a state, and any linear combination of that state is also a state of a system. So this is also the state of a system. And obviously, this principle is nothing but known as principle of superposition. So, if you have different state and you will be superimposed to one state to another state, and this is the linear superimposition, what you will get? You will get a state of a system. So somehow from postulates 1, we try to introduce the wave nature of a particle, because you have all information from your wave nature, or that interference and diffractions everywhere, that superposition of wave will be a wave, superposition of electric field will be the electric field. Similarly, the superposition of a state will be a state. And there is one favorite question to from students. Sir, what is physical meaning of a state? State is state. That's all. Similarly, if you will tell what is, if in the classical mechanics, the state is x and px, they are the state, they are defined state. Similarly, into the quantum mechanics, the state belongs to the Hilbert space associated to the system, and that is the state. So there is not any need to ask what is physical meaning. Physical state is state, that is the answer. Because once you know the state, you can easily calculate each and every physical quantity. That is the purpose of all defining the state. I am just moving a different way from quantum mechanics to understand all this thing. Suppose in a thermodynamics, what are the state? The pressure, volume and temperature are the state. Why we have defined the pressure, volume and temperature as a state? Because if we know the pressure, volume and temperature of a state, we can define any thermodynamical quantity. This is all purpose of a state. Similarly, in the classical mechanics, if you have a state such as position and momentum, and if you know the position and momentum of a particle at some particular point of time, then obviously you can define any physical quantity of that particular system. Similarly, if we define the state of a system, and obviously this state will change with the time, so obviously it will be a function of time, because we have to see how it will evolve with the time, and that is the ultimate purpose. So the state is all about the superposition of a state is the state of a system. And yes, all belongs to the same Hilbert space, means they will follow the closure relation. But yes, we are physicists. Then we must try to understand things physically. But before I am going to the next level, if you have any doubt, you can just ask me. Then I will go for a next level to definition of what is physical into this particular state. Not definition, what is physical, how can understand all this thing. So if you have any doubt, you can just ask me. Okay. Now, if you construct the state, suppose I have constructed one state, and how we will construct, that is different issue. But right now we are just giving the definition. Now, if we construct the state psi, and obviously we can write it in form of function, we can represent this state in the form of ket, you can represent this state in form of column vector ket as a function, any n number of ways are there. So this is the state of a system. Obviously we can write as a functional form, and let's say this is belongs to some one-dimensional system, and so this is psi x. So if we can define the state of a system, then mod psi square can be treated as, and mod psi square, and you can write something like this: if mod psi square dx integrate from minus infinity to plus infinity is equal to 1, then mod psi square is identified as probability density. And what is this probability density? It will tell probability, and what is probability, and this mod psi square dx is nothing but probability to find the particle between x to x plus dx. And you can just write this thing as something, you can just write rho x. So rho x is nothing but probability density. Sometimes we can write rho x, sometimes we can write fx. So don't worry, this is nothing but probability density. So now this is a physical. So what we have done, we construct a state, and that is very abstract, that is mathematical. And once you are taking the mod psi square, this is identified as probability density, and mod psi square dx is nothing but the probability to find the particle between x to x plus dx. This is the purpose of basically defining the state. What will be probability that particle will be at x to x plus dx? How we can find it? And obviously this probability will belongs to 0 to 1. That is a fraction. You know all this thing. We have the behavior of particle actually probabilistic in nature. Even we cannot say precisely where is the particle. We have to associate some probability such that particle belongs to x to x plus dx. So what is the purpose of a state? The first purpose of to defining the state is all about to defining the probability density. Once we define the probability density, we can easily calculate that what will be chance that particle will be there or not there. So this is a very interesting thing. So if you have any doubt, you can just ask me.
So mod psi square is probability density or mod psi square times dx?
Mod psi square is probability density. Mod psi square dx is probability. It
Okay,
is
sir.
directly written. It is probability. Okay? Means, just look at here. Means, if I will ask you, what will be probability such that your particle belongs to A to B. Suppose I'm taking the equal sign. What will be chance such that particle belongs to A to B? What you will do? You will just do A to B mod psi square dx. This is favorable chance by total chance. And total chance is minus infinity to plus infinity mod psi square dx. Isn't it? And if this is 1, then obviously it is normalized. But if it is not normalized, then obviously you have to calculate this particular value. So this is a definition of probability. So if you have defined probability, you can just say what will be chance that particle is between A to B. So this is favorable chance, and this is total chance. So what will be total chance? Total chance is always 1. Yes, particle will be somewhere between minus infinity to plus infinity, and if you will all add it, you will add the all chance, you will get 1, and this is what you want to calculate. Obviously this is a number and this is a ratio, in we can calculate in term of percentage or ratio. Okay, so this is the all about postulates 1. So if you want to know about postulates 1, this is the state. The superposition of a state is also a state, and yes, the purpose of this state, the first purpose actually, the first purpose of this state, that you can construct the probability density. This is very interesting. Okay, so let's go for postulates 2. So should I go ahead, or you have any problem? If you have any doubt, just ask me, because I don't know are you getting or not.
सर ये फेवरेबल एक बार बता दीजिए.
Sorry,
फेवरेबल बता
favorable. Sorry, favorable means जो आप कैलकुलेट करना चाहते हो. You just want to calculate that what will be chance, what is favor, what is favorable chance, so that particle will be between A to B. So this is your favorable thing and this is your total thing. So this is the, what is definition of probability? The favorable outcome by total outcome. This is the definition of probability, isn't it? So let's go for postulates 2, and this is very interesting. Let's try to go for postulates 2. Don't worry, if your after your postulates will be finished, I will give you some writing. Okay, so don't worry, everything is written into that particular document. So I will give you, but before postulates, it is not important. Once I will finish the postulates, I will give you one writing, step by step, everything is written there. Okay, so let's go for postulates 2. So obviously, the purpose of defining the state is all about to measure the physical quantity. That is the main purpose. Obviously, we have extra information of the probability density, but main thing what we want to define a physical quantity. So if you know the state, how you can define the physical quantity in a quantum mechanics? So this is physical, the second postulate is all about physical measurement of state. Obviously we have state psi. So in first postulates we have defined a state psi. So whenever you will attempt the problem, your first duty is that you have to define what is psi. Either it is given into examination or you have to construct the psi. These two things can be happen. Up to this, the people are given the state, but sometime you have to construct the state. Let's say this is the state and this is well defined. The state is well defined. This is state. What I want, I just want to measure a physical quantity. So their associated operator A with physical quantity. Obviously, please, if I am just giving you an analogy, suppose you want to measure a length in a lab, you will use the scale. Scale is your one tool. Suppose you want to measure the mass in a lab, you will use the weighing machine. So similarly in a quantum mechanics, for every physical quantity there associated a operator. So every physical quantity, and that is not same operator is associated to everything. No, if you want to measure the energy, there is a one particular operator which is associated to the energy. If you want to measure the momentum, there is another operator that will use to measure the momentum. If you want to change sign x to minus x, there is an operator named as parity operator. So there are n number of operators. So look at here. So there associated operator A with a physical quantity. So there is operator A. So you can, I am just giving you example. For example, to measure energy, there is Hamiltonian operator. So there measure energy, there is Hamiltonian operator. And what is Hamiltonian operator? Hamiltonian operator is nothing but px square upon 2m plus vx. So this is the Hamiltonian operator. So to measure the momentum, you have momentum operator. And what is definition of momentum operator? Minus ih cut d upon dx. So this is definition of momentum operator. So you have n number of operators. And these physical quantities identified as observable. These are identified as observable. That thing, you that observable can be observed by the operator. So these observable is have some associated some mathematical quantity that is operator. So this is first definition of operator. And obviously this is n cross n operator. And we just also explore lot of thing about this. Up to this, are you getting this? Are you getting all this thing? Then we will go for the next level. Now, let's go for the measurement quantity. So first we have to define the physical quantity, and then we have to just, this is the algorithm. First you have to define physical quantity, or observable, and they're associated a operator. They're associated a mathematical operator. Whatever with the thing, if you want to change the particle from one is placed to another place, x1 to x2, you have exchange operator. You have n number of operators. So don't bother about it. It will be either defined and nothing, you have nothing to do with this thing. The examiner will give you, and there are n number of operators. The big people have defined this kind of operators. You have number operator, raising operator. Suppose you want to raise the particle from one level to another level, there is raising operator. There are a number of, whatever you want to do into quantum mechanics physically, there is associated operator. Now, so the postulates is very interesting. If A will measure on state psi, if A will measure on state psi, and psi is state, A will measure on state psi, the measurement is eigenvalue of operator. The measurement is eigenvalue of operator and corresponding eigenvectors are identified as eigenstate. So corresponding eigenvectors are eigenstate. So what is the second postulates? The second postulates is very simple. It will just tell you about the eigenvalue and eigenstate of operator A. So we can define A phi n is equal to an phi n. This is all about operator, eigenvalues of operator. Now, so this is the eigenvalues. Now please, this is the measurement. The eigenvalues are measurement. So this is eigenvalue and this is measurement. And this is identified as eigenstate. Now you have to construct the eigenstate. You have to construct the eigenstate such that one should find the eigenstate such that phi n summation over n must be equal to 1. Means the eigenstate must form a complete relationship. And it will follow the completeness relationship. What is this? Whatever with the eigenstate you will find, that must be follow completeness relationship. That should be the completeness relationship. Why we need completeness relationship? Why you need completeness relationship? It's a very interesting. Because you have a state. Now we have two things. One is a state, another is eigenstate. So there is a state. Now, if you have completeness relationship, then any state can be written in a basis of eigenstate, and that will be the orthonormal basis of eigenstate. We can write something as phi n psi summation over n, and obviously what we have written, psi can be written as summation over n cn phi n. And what is cn? Cn is nothing but phi n psi. So deliberately, if A is operator associated to the physical quantity, we construct the eigenstate which will be orthonormal in nature such that it can form a completeness relation. It can form a completeness relation. So why I have told you in the last class that whenever you are getting the matrix and you have to find the eigenvalues, try to find it as a orthonormal, as a eigenvectors, try to find it as a orthonormal eigenvector such that it can make a completeness basis. Obviously, if there is non-degeneracy, there is not any problem. But if there is degeneracy, there is huge problem. Yes, we have seen in the last class. Now, up to this, are you getting all this thing? I will go to next level.
Excuse me, sir.
Yes.
Sir, here on which state operator A has operated, what is phi n over here?
Phi is the eigenstate of A.
Okay, sir.
This is, you have to calculate this thing. This is phi n. Phi n is eigenstate and psi is state. Please, I am using this notation. Psi is state and phi n is eigenstate. Okay. Now, just look at this information very carefully. Just look at this thing. Eigenvalue and eigenstate. Look at this thing very carefully. What you have, what is physical measurable quantity? An is the physical measurable quantity, isn't it? An. And every physical measurable quantity must be real. It must be real. You can have always real momentum, you can have always real energy. So I have to construct an operator whose eigenvalue must be real. This is one more important thing. So the next information is very interesting. Hence, the measurement, hence physical measurable quantity is real, then eigen value must be real. So it is necessary that operator A is Hermitian. Why Hermitian? Because if operators are Hermitian, then its eigenvalue must be real. So always, if operators are associated to physical quantities, it must be Hermitian in nature. Hermitian is what? A dagger is equal to A. So this is all about Hermitian. So always you have Hermitian operator. So this is the thing. So in a first postulates, we have defined the state. In the second postulates, we have defined eigenvalue and eigenstate. There are two different things. Eigenvalue and eigenstate must follow this particular relationship. And yes, you can construct a state in a basis of eigenstate. One can write a state in a base in orthogonal basis of eigenstate. Orthogonal basis of eigenstate. And now the most important thing is there. Every eigenstate can be state of a system, but vice versa is not true. So every eigenstate can be treated as a state of a system, but it is not necessary that every state is eigenstate. So you can have this particular information. Your eigenstate can be a state. There is not any problem. But it is not necessary your state will be eigenstate. It may be eigenstate, it may not be eigenstate. Because for the eigenstate, you have to follow this particular rules and regulation. So let's try to understand this thing with an example.
सर आपने ये ऑर्थोगोनल के बाद क्या लिखा है?
Orthogonal basis of eigenstate. Orthogonal basis of eigenstate. यही तो कर रहे हैं ना, है ना? Orthogonal basis of eigenstate. ये देखो, ये जो के है ना? You can write something like this. So you will see in the examination, they will give you state in a basis of eigenstate. Or you have to write a state in a basis of eigenstate. This is the thing. So what we have to do? Very simple. You have given one state. If you want to measure energy, then there is Hamiltonian operator. Then you have to write a state in a basis of you have to write the state in a basis of eigenstate of Hamiltonian operator. That's it. Second, suppose again same state is there, and if you want to measure momentum, then what you have to do? You have to write this state in a basis of eigenstate of momentum. Suppose there is suppose you have parity, you have to measure the parity. Then first you have to find what will be eigenstate of parity operator, and then you have to write the state in a basis of eigenstate of parity operator. So postulates 1 will be state and postulates 2 will be the eigenvalue and eigenstate. Let's go for one very simple example such that you can just understand what we are going to do.
Hello, sir. Sir, what have you written in last line after but?
Vice versa is not true. Means vice versa का मतलब नहीं समझ में आता है.
No, sir.
Every
I
eigenstate,
understand, but
every eigenstate can be a state of a system, but यहाँ लिख दे रहा हूँ. But it is not necessary that every state is eigenstate. Now it's clear?
yes, sir.
Okay. Actually, for quantum mechanics, at least we need 2 boards. In one board, it is very difficult.
We have to find both the eigen state as well as the eigen value. No?
Yes, yes. You have to find. Look at one example. Very good example. Suppose the operator A is defined as, let's say, A0, 0, 0, 2 A0. Suppose operator A is defined as. Okay. And this is your operator A. And suppose you will measure on state psi 1. And let's say psi 1 is 3, 5. This is what will measurement? What will measurement? So what you have to do? You have to just find the eigenvalues. You have to just find the eigenvalue and eigenvector. So what will be eigenvalue? So let's say eigenvalue is A0 because it is diagonal element, diagonal matrix. So A2 is 2A0 and this is phi 1 and phi 1 is 1, 0. And what is phi 2? Phi 2 is 0, 1. You can just find this thing from, you have to calculate this. You have to calculate with this particular formula. A minus lambda I must be equal to 0. and then you have to find all this thing. So what is eigenvalues? So obviously, if A will measure on a state this, what will be the measurement? The measurement is A naught or 2A naught. You will give the measurement is A naught or 2A naught. This is the measurement. Suppose the same operator is going to measure psi 2 and psi 2 is 819. What will be measurement?
A naught to A naught, same.
Exactly, A naught to A naught. That's it. You need not to apply. This is not all about the postulates. A psi 1. Suppose you are going to apply A on A naught 0, 0 to A naught. And you will write here 3, 5. And you will get something. What you will get? 3A naught and 10A naught. And you will suppose take A naught common, and here is 3 and 10. Sorry, this is not eigenvalue, eigenvector. You need not to do this all thing. Extremely sorry. What you have to do, you have to just find the eigenvalue and eigenvector, this thing, for postulates 2. You have to just find the eigenvalue and eigenvector. Here is, you have just find what is the eigenvalue and what is the eigenvector. These are the eigenvalues. There are 2 eigenvalues, and these are the eigenvector. And what is measurement is the eigenvalue. So measurement is simple eigenvalue. So either you will measure on psi 1, you will get A naught or 2A naught. Look at this, or is very important. Either you will just, the quantum mechanical language is very interesting. If I will tell you that measure A on state psi 1, I am not saying operate A on state psi 1, please. This is all about operation. What I am saying, measure A on state psi 1. Measure A on state psi 1 means you have to that calculate that eigenvalue of the operator. So what is eigenvalue? I have deliberately taken it as a this diagonal matrix, such that eigenvalue is the diagonal element. So the measurement is either A naught or A naught. So you will write the measurement is either A naught or 2A naught. Here again you will write the measurement is either A naught or 2A naught. The measurement is either A naught or 2A naught. Again you have third one. Let's say psi 3. The again next state. Let's say this is I and minus I. It may be a state. What is measurement? What is measurement?
A naught to A naught.
A naught or 2A naught. A naught or 2A naught. Again, measurement is A naught or 2A naught. Now your general, a very natural question is that if A will measure on psi 1, the measurement is A naught or 2A naught. A will measure on psi 2, the measurement is A naught or 2A naught. A will measure on psi 3, the measurement is A naught or 2A naught. Then what is purpose of different state? Why you are writing this psi 1 as 3, 5? What are meaning of this particular number? That can be answered by postulates 3. Okay, so I will take up postulates 3 into next class, and till then you can just revise all this thing. So once we will finish the postulates, I promise you I will give you a wonderful handout and with some problems also, such that you can just revise all this thing beautifully. Okay, but before that, be confused. Be confused, don't worry. If you are confused, don't worry. The subject is something like that. Okay, either a naught or 2a naught. This is something like when you are tossed the coin, what you will get? You will get either head or tail. That's it. Similarly, this is something like a coin. What you will get? You will get either a naught or you will get either 2a naught. That's it. So I hope you enjoy this thing. If you have any doubt, you can just ask me. Just 2 minutes.
Excuse me, sir.
Yes.
Sir, phi 1 and phi 2 will be the eigenstate in this question. Na? 1, 0,
Yes.
and
Yes.
2.
Phi 1, phi 2. 1, 0 and 0, 1 is the eigenstate. This is the state. This is a state. This is state named as psi 1. This is also a state. This is also a
Okay.
state. But what is eigenvalue and eigenstate will be same. Okay.
Okay, sir.
And these are eigenvalue and eigenstate. Don't worry. Eigenstate. Okay. Don't worry.